discussion will focus on iterated integrals, or sometimes we call it as multiple integrals. Now, what is iterated integral and how does it differ with an ordinary integral? Actually, an iterated integral is the result of applying integrals to a function of more than one variable in a way that each of the integrals considers some of the variables given as constant. Okay, recall that in Math 146 or in Calculus 1, we learned that if we are given, say, a function z which is in terms of x and y, function of x and y, we can get the partial derivative with respect to x and the partial derivative with respect to y. Now, getting the partial derivative with respect to a variable sets the other variable as constant. So this is what we do also when evaluating iterated integral or multiple integrals. Okay, when evaluating with respect to a variable, all the other variables are held as constant. So if we have f, which is a function of x and y, and it is continuous within a rectangular region, okay, where x is within the closed interval from a to b and y is within the closed interval from c to d. Okay, by the way, the region R here is, okay, means that x goes from a to b and y goes from c to d. Okay. Now, we can represent the double integral of f of xy times the differential of a. Okay, differential of a, since the differential of a may be either dx dy or the differential of a is dy dx. Now, if we are going to show the rectangular region R in the xy plane, let us say we have this rectangular region, okay, this is the rectangular region R, into consideration, okay, the value of x goes from a to b and the value of y goes from c to d. Okay, we have the closed interval from a to b and closed interval from c to d. This is the coverage of the rectangular region. Okay, hence, going back, the double integral of f of xy times the differential of a, in which the differential of a is the rectangular or the region or the element here, where this is dx and this is dy. Okay, when we say the differential of a is dy dx, okay, we evaluate first the integral from the lower to the upper, okay, similar to evaluating the integral using the vertical element, and dx, okay, evaluates the integral from a to b, horizontal. So if it is dy dx, vertical first and then horizontal. On the other hand, if we have the differential of a equals dx dy, okay, horizontal first from left to right, then lower to upper. Now, if we have a rectangular region, then the order is not really that critical. It may be dy dx or dx dy, meaning the double integral of f of xy times the differential of a over the region R is equal to the double integral of f of xy dy dx where y goes from c to d and x goes from a to b. And it is also equal to the double integral of f of xy dx dy, reversing the order, where the inner integral is in x and x goes from a to b, y goes from c to d. So the integral of f of x y dy dx, where y goes from c to d and x goes from a to b, means that we will evaluate the inner integral first in y, and the result becomes the integrand of the outer integral in x. On the other hand, evaluating the integral of f of x y dx dy, okay, where x goes from a to b and y goes from c to d, it means that we will evaluate the inner integral first in x, okay, within the limits of integration from a to b, and the result becomes the integrand of the outer integral in y. Now, we have to take note that when performing the inner integral, like here in y, the other variable x is temporarily held as constant. On the other hand, if, excuse me, we will evaluate the integral where the order is dx dy, the inner integral is evaluated in x and y is temporarily held as constant. So that is what we do when we evaluate iterated integral. Now, this is when the case is a rectangular region. We can either do it vertically simple. When we say vertically simple, the differential of a is dy dx. We go first lower to upper, then left to right, or horizontally simple, dx dy, meaning going first horizontal from left to right, or then from lower to upper. And uh, these integrals are equal. On the other hand, if we have a non-rectangular region, then this will give us the double integral of f of xy if we have vertically simple dy dx. Y will go from g1 to g2, and g1 and g2 must be independent of y, and if it is independent of y, then g1 and g2 must be in terms of x. Okay, and the outer limit of integration a and b must be independent of y and x. Now, on the other hand, evaluating the integral in the order dx dy horizontally simple, okay, the inner limits of integration h1 and h2 must be independent of x. And if it is independent of x, it must be in terms of y. And the outer limits of integration c and d must be independent of y and x. Therefore, c and d here must be constant. So we have to remember that the outermost limit of integration must be independent of all the variables of integration. Therefore, the outer limits of integration must be constant. And again, we have to take note that when evaluating the inner integral, the other variables are held as constant. Like when evaluating the integral in y, the other variable x is held as constant. When evaluating the integral in x, the other variable y is temporarily held as constant. Now, before we start with some illustrative problem on how to evaluate iterated integral, let us go over the different properties of double integrals, which are in a way similar to the properties of an ordinary integral, ordinary definite integral. Okay, now if we have first, we have the first property that if we have a constant factor in the integrand, let us say a constant c, we can write the constant factor c before the integral sign. Okay, and if we have sum or difference in the integrand, we can express the double integral as sum or difference of double integrals. Okay, now we have to take note, no, that again, no, I forgot to mention earlier that it is double integrals, no, if we have uh, two symbols of integration. Okay, meaning we have this symbol, two symbol of integration, double integrals over the region R. This is a double integration. Now for triple integration, which we will consider later over the region R, okay, this is f of x y times the differential of a, where the differential of a can be in the order dx dy or dy dx depending on the circumstances or the circumstance rather. Now, if we have triple integral, then the element is dy dx dz or in any order, or it is equal to the differential of v. Now, considering the first example, let's consider the first example. Let us say we have the double integral of 20 minus xy dy dx in the order dy dx, where y goes from 2 to 4 and x goes from 1 to 2. Now, here, the region R is the region, the rectangular region, where x is greater than or equal to 1, less than or equal to 3, the outer limits of integration, and the inner limits of integration are 2 and 4, so y goes from 2 to 4. If we are interested on how it looks on the xy plane, the rectangular region, okay, if this is the x-axis and this is the y-axis, y goes from 2 to 4, so 1, 2, 3, 4. Okay, this is 2 and this is 4. And x goes from 1 to 3. Hence, the rectangular region is this region. Okay, the shaded region, rectangular region, where x goes from 1 to 3 and y goes from 2 to 4. So we can represent the differential of a as an element here. This is the element where the sides are the differential of x and differential of y. So we are going to consider that the differential of a is dy dx, but we can also consider that the differential of a is dx dy. In the problem, okay, we are asked to evaluate the integral in the order dy dx. Hence, it means that we will evaluate the inner integral from the lower limit to the upper limit. So we are going vertical. Okay, then the outer integral in x, no, will be evaluated from 1 to 3, from left to right? So that this is vertically simple since we will do first vertically, okay, integrate in y from lower to upper, and then evaluate the integral in x from left to right. Okay, so let us evaluate the integral, the double integral of 20 minus xy dy dx, where y goes from 2 to 4 and x goes from 1 to 3. Excuse me. So hence, to evaluate the double integral, we consider first the inner integral, the integral of 20 minus xy dy, okay, where y goes from 2 to 4. So evaluating, this is equal to, okay, we write the outer symbol of integration. Okay, evaluate the integral of 20 minus xy dy, holding x as constant, since we are evaluating with respect to the variable y. So the other variable x will be held as constant. And the integral of 20 dy is 20y minus integral of x dy, xy dy. X is held as constant, so the integral of y dy is y squared over 2. So x y squared over 2, and this must be evaluated from the lower limit 2 to the upper limit 4. Okay, meaning y is equal to 2 to y is equal to 4. Then do not forget to write the differential of x, okay, which will indicate that the outer integral must be evaluated in x. So we have the integral from 1 to 3, okay, evaluating the resulting inner integral 20y minus xy squared over 2 when y is equal to the upper limit 4. Okay, take note, upper minus lower. So that gives us 20 times y. So 20 times 4 is 80 minus 4 raised to the second power is 16 over 2 is 8 times x. Okay, so that gives us 8x minus the value of the integral when y is equal to the lower limit at 2. So 20 times 2 is 40 minus when y is equal to 2, 2 square is 4. 4 over 2 is 2 times x gives us 2x. Okay, times the differential of x. And let us simplify the integrand, the resulting integrand, which is the result of the inner integration. It becomes the integrand of the outer integration in x. And 80 minus 40 is 40. Negative 8x minus minus 2x is negative or minus 6x dx. Okay, we are now ready to evaluate the integral in x. Okay, integral of 40 dx is 40x minus the integral of 6x dx is 6x squared over 2. Now 6 over 2 is 3. Okay, which will give us the simplified form of the integral as 3x squared. And we must evaluate this from the lower limit x is equal to 1 to x is equal to 3. Okay, hence we have when x is equal to the upper limit 3, 40 times 3 is 120 minus 3 raised to the second power is 9 times 3 is 27 minus the value of the integral at the lower limit 1. So 40 times 1 is 40 minus 3 times 1 square is 3. Okay, and simplifying further gives us 120 minus 27 minus 40 minus 3 is 37. Okay, we can actually remove the grouping symbol. And this is equal to 120 minus 27 plus 37 is 64. And 120 minus 64 is 56. Okay, therefore, the double integral is equal to 56. Now, we can actually solve the integral the other way around, no, meaning reversing the order. Instead of evaluating the integral in the order dy dx, then we can also evaluate it in the order dx dy, or the differential of a is dx dy. Hence, if we will do that, no, then we have the double integral of 20 minus xy dx dy, where x will go from 1 to 3. This time, the inner limits of integration goes from 1 to 3, okay, and the outer limits of integration goes from 2 to 4. And please take note that this will also give us the integral equal to 56. And when evaluating this integral, we perform the inner integration first in x, thus holding y temporarily held as constant. Okay, let us go further, and this time let us consider the second example. Compute the iterated integral for the function f of xy is equal to 4x cubed plus 6xy squared on the rectangular region R. Okay, okay, close interval x is the close interval from 1 to 3, and y goes from -2 to 1. Now we can also write the region R, okay, as x going from 1 to 3, and y goes from -2 to +1. Okay, and in the xy plane, the region R is rectangular, where y will go from -2 to 1, and x will go from 1 to 3. And since this is rectangular, the differential of a may be either dx dy, or the differential of a is dy dx. Okay, we can either do in the order dx dy or dy dx. Okay, let us consider the order dx dy. Okay, meaning we will evaluate the double integral over the region R of f of x, y times the differential of a, and we will consider the order where the differential of a is dx dy. So f of xy is 4x cubed plus 6xy squared dx dy. So the inner variable of integration is x. Therefore, the limits of integration will go from 1 to 3. X going from 1 to 3, and the outer limits of integration goes from -2 to +1. So to evaluate the integral, we will evaluate the inner integral first in x, and If we will evaluate the integral in x, the variable y will be temporarily held as constant. Hence, this gives us, okay, integral from -2 to 1. Integral of 4x cubed dx is 4x to the fourth over 4, or simply x to the fourth, since 4 will cancel. Okay, and in here, 6x is constant. Okay, x is temporary, sorry, 6y squared is constant. No, y is temporarily held as constant since we are evaluating the integral in x. So the integral of x dx is x squared over 2. So 6 over 2 is 3. So that will give us 3x squared, okay, times the constant y squared. And this must be evaluated from the lower limit 1, so x is equal to 1 to x is equal to 3 dy. Okay, hence, this will give us integral from -2 to 1. Okay, let us evaluate the resulting integral from the lower limit x is equal to 1 to the upper limit x is equal to 3. Of course, it is equal to upper minus lower. Value of the integral at the upper limit minus the value of the integral at the lower limit. So when x is equal to 3, okay, 3 raised to the fourth power is 81. So this gives us 81. And when x is 3, 3 squared is 9 times 3, 27, plus 27 y squared. Okay, then minus the value of the integral when x is 1. So when x is 1, 1 raised to the fourth is 1, plus when x is 1, we have 3 times 1 squared times y squared will give us 3y squared dy. Okay, and then we simplify the resulting integral, which becomes the integrand of the outer integral in y. So we have integral going from -2 to 1. Okay, we have 81 minus 1 is 80. And 27y squared minus 3y squared is 24. Plus 24y squared dy. We may also factor out the common factor 8 if we want to factor out the common factor 8. Okay, or if you want, you can just continue integrating. So if you will continue integrating, the integral of 80 dy is 80y, 80 times y, okay, plus the integral of 24y squared dy is 24y cubed over 3, and 24 over 3 is 8. So plus 8y cubed. And this must be evaluated from the lower limit y is equal to -2 to y is equal to 1. Okay, now please take note again that we have here common factor which is 8. Now, it will be easier if we will factor out the common factor 8 and then just evaluate 10y plus y cubed within the limits of integration from -2 to 1. So we have 8 times, when y is equal to the upper limit 1, 10 times 1 is 10, okay, plus 1 minus the value of the integral at the lower limit, -2. When y is equal to negative 2, 10 times negative 2 is negative 20. And negative 2 raised to the third power is negative 8. Okay. We have 8 times the quantity. That gives us 11. This is negative 28 minus minus is positive. So plus 28, and we have 8 times 11 plus 28 is 30, 39. And if we will multiply 39 by 8 will give us, okay, 72, 7, 24, 3, 31, 312. So the integral is equal to 312. Okay, and in here, we consider the differential of a equals dx dy in the order dx dy. But we can also solve this in another way, that is considering the differential of a equals dy dx. Of course, it must give us 312. So let us try it this time. Okay, in the first example, I told you to consider uh, the other order. Okay, we did dy dx, and to practice, you can do the order dx dy. Okay, so another way to evaluate the integral over the region R, okay, if we have the integral of 4x cubed plus 6xy squared times the differential of a in the order where the differential of a is dy dx this time. So we will have the double integral of 4x cubed plus 6xy squared. Okay, this time we will have dy dx, and y will go from negative 2 to 1, x will go from 1 to 3. Hence, we will evaluate first the inner integral in y and holding x temporarily held as, holding x as constant temporarily. So integral from 1 to 3. Okay, let us evaluate the integral in y. Take note that x is temporarily held as constant. So integral of 4x cubed, this is a constant, dy is 4x cubed y. Okay, and since x is temporarily held as constant, we will just evaluate the integral of y squared dy, and the integral is y cubed over 3. So 6 over 3 is 2. So 2x y cubed, and this must be evaluated from y is equal to negative 2 to y is equal to 1. Okay, then we multiply this by dx. Hence, this gives us, okay, the integral from 1 to 3, okay, and when y is equal to 1, okay, we replace y by 1, thus giving us 4x cubed plus, when y is equal to 1, we have 2x times 1 cubed is 2x, so plus 2x, minus the value of the integral at the lower limit, negative 2. Okay. Let me write this properly. Okay. So this time we will evaluate the resulting integral at the lower limit, y is equal to negative 2. So replacing y by negative 2, 4 times negative 2 is negative 8. So negative 8x cubed. Okay. Negative 2 raised to the third power is negative 8. Negative 8 times 2 is minus 16. 16x. Okay, then close times the differential of x. And then let us simplify integral from 1 to 3. Combining similar terms, we have 4x cubed minus minus, so that gives us positive. 8x cubed gives us 12x cubed. Then 2x minus minus 16x. Okay, so 16 plus 2 gives us 18. So positive 18x dx. Okay, let us factor out the common factor muna. We have 12 and 18, so common factor is 6. Okay, integral from 1 to 3. Okay, so since we factored out 6, then this becomes 2x cubed. Okay, then plus 3x dx. And we can now evaluate the integral in x. That gives us 6 times integral of 2x cubed dx is 2x to the fourth over 2 over 4 rather. So by cancellation, that will give us x to the fourth over 2. X to the fourth over 2, since 2 and 4 will cancel, now giving us 2 in the denominator. Then plus the integral of 3x dx, which is equal to 3x squared over 2. So 3x squared over 2, and limit will go from 1 to 3. Okay, hence this is equal to 6 times. Okay, evaluating the integral at the upper limit 3. Okay, 3 raised to the fourth power is 81. We have 81 over 2 plus 3 square is 9 times 3, 27. 27 over 2, okay, minus the value of the integral when x is equal to 1, and when x is equal to 1, it will give us 1 half plus 3 over 2, okay, close, close. Hence, we have 6 times 81 plus 27 will give us 108, right? So 108 over 2, okay, minus 1 half plus 3 over 2 is 4 over 2, and 4 over 2 is 2. Okay, we have 6 times 108 over 2 is 50, 54. 54 minus 2 is, okay, 6 times 52, and multiplying 52 by 6 will give us 312 as well. Of course, we must get the same answer. Previously, okay, we were able to evaluate the integral, okay, where the differential of a is dx dy, and it gives us the double integral equals 312. Of course, if we will reverse the order, okay, making or using the differential of a equals dy dx. Now, since the region is rectangular, then it must give us the same value of the integral. Okay, the integral is equal to 312. Okay, so that is how we reverse the order of the integral. And there is no problem here since we have a rectangular region. We can either do upper to lower to upper, then left to right, or left to right, then up, lower to upper. Okay, we can do vertically simple or horizontally simple, okay, without problem if we have a rectangular region. Okay, so let us consider this time another example. And the third example is no longer a rectangular region. Okay, we have the double integral of xy squared dy dx, where y goes from negative x to x squared and x goes from 0 to 1. Okay, look here. Look at the limits of integration, the inner limits of integration. Okay, the inner variable of integration is y, therefore the inner limits of integration must be independent of x, and it is independent of x. Okay, outer limits of integration must be independent of x and y, therefore the outer limits of integration must be constant. Okay, so we can now proceed to the evaluation of the double integral of x y squared dy dx, where y goes from negative x to x squared and x will go from 0 to 1. Okay, by the way, if we are going to write or indicate the region R, okay, we have the region R, which is non-rectangular, where x goes from 0 to 1 and y goes from negative x to x squared. Okay, so this is the region R, which is non-rectangular. So to evaluate the integral, we perform the inner integration first, no integral with respect to the variable y. Therefore, x is temporarily held as constant. Hence, this will lead to integral from 0 to 1, okay, holding x temporarily as constant rather. The integral of y squared dy is y cubed over 3. So that will give us x y cubed over 3, okay? And we have to evaluate this from the lower limit y is equal to x to, by the way, this is negative x, sorry. Y is equal to negative x to x squared, okay, times the differential of x. Okay, it will be more convenient if we can write 1/3 before the integral sign. So writing 1/3 before the integral sign, okay, gives us integral from 0 to 1, and we will evaluate x y cubed, where y goes from negative x to x squared, okay? Then do not forget the differential of x. Hence, we have 1/3 integral from 0 to 1, okay? Evaluating the resulting integral xy cubed from y is equal to negative x to x squared, okay? When y is equal to x squared will give us x times the quantity x squared raised to the third power, okay, minus the value of the integral when y is equal to negative x. So minus x times negative x raised to the third power dx. Hence, we have 1/3 integral from 0 to 1. The x squared raised to the third power is x to the 6 times x will give us x to the 7. Okay. Negative x raised to the third power is negative x cubed. Minus minus is plus. So plus x raised to the fourth power. Okay, dx. And we can now evaluate the integral in x. Okay, 1/3 times the integral of x to the 7th dx is x raised to 8 over 8. Okay, then plus the integral of x to the fourth dx is x raised to 5 over 5. And we have to evaluate this from the lower limit 0 to the upper limit 1. Hence, we have 1/3, okay, times, okay, evaluating the integral when x is equal to the upper limit 1 will give us 1 over 8 plus 1 over 5 minus the value of the integral at when x is equal to 0, so minus 0. Okay, hence we have 1/3 times. We can get the common denominator. Of course, the common denominator is 40. Okay, 40 by 8 will give us 5 times 1, so 5. Okay, and this must be 8. Okay, so we have 5 plus 8 is 13 over 40 times 3 will give us 120. Okay, therefore, the double integral of xy squared dy dx, where y goes from negative x to x squared and x goes from 0 to 1, is 13 over 120. Okay, so this time we considered a non-rectangular region. And we cannot simply reverse the order. We have to do something in reversing the order, and we will come to that later. Okay, let us have the next example. Okay, this time we will consider evaluating the integral of x sine of y in the order dx dy. And x goes from 0 to cosine of y goes from 0 to pi over 3. Look here, the inner variable of integration is x. Therefore, the inner limits of integration must be independent of x. Okay, so cosine of y is independent of x, 0 is independent of x, and the outer limits of integration are constant. Okay, independent of the variables x and y. So the region R is the region where x goes from 0 to cosine of y, and y goes from 0 to pi over 3. Okay, so we are now ready to evaluate the double integral. Okay, we have the double integral of x sine of y dx dy, where x goes from 0 to cosine of y and y goes from 0 to pi over 3. Okay, hence we evaluate the inner integral first with respect to x, therefore holding y as constant. So we will take sine of y as constant. Okay, therefore we have the integral from 0 to pi over 3. Okay, integral of x dx is x squared over 2 times the constant sine y. So x squared over 2 times sine of y, and this must be evaluated from the lower limit x is equal to 0 to x is equal to cosine of y, okay, then dy. Okay, now we can also write 1/2, okay, the constant 1/2 before the integral sign. And doing that, we have 1/2 integral from 0 to pi over 3 of x squared sine of y, and this must be evaluated from x is equal to 0 to x equals cosine of y. So evaluating the resulting integral at the upper limit cosine of y, we have to replace x by cosine of y, thus giving us 1/2 integral from 0 to pi over 3 of cosine of y raised to the second power is cosine square of y, okay, times sine of y minus the value of the integral when x is 0. Of course, when x is 0, okay, that will give us the integrand equals 0, or in the integral rather equals 0 times the differential of y. Okay, hence we have 1/2, okay, integral from 0 to pi over 3 of cosine square of y sine of y dy. And we can evaluate the integral by power formula. And if you will do power formula, of course, we have to let u is equal to cosine of y, whose differential is negative sine of y dy. Okay, therefore, we have a correction factor which is negative sign. Okay, hence, this is equal to, okay, we write the correction factor -1, okay, here. The negative sign written here is the correction factor. Okay, and we have 1/2. And evaluating the integral of cosine square of y negative sine of y dy by power formula gives us cosine cube of y over 3. And this must be evaluated from the lower limit 0 to the upper limit pi over 3. Okay, so we have negative 1/2 times. Okay, when y is equal to the upper limit pi over 3, that must give us cosine of pi over 3 raised to the third power. And cosine of pi over 3 is 60, cosine of 60 is 1/2. So we will have 1/2 raised to the third power, okay, over 3. Okay, we can also factor out 1/3. And if we will factor out 1/3, no, let us do that. Okay, to make the computation more simple. Okay, so this will give us negative 1/2. Okay, then we will factor out 1/3, so times 1/3 here. Okay, times the quantity. Okay. So times the quantity. Okay. Evaluating cosine cube of y when y is pi over 3 is cosine of pi over 3 raised to the third power, or cosine of 60 raised to the third power, and cosine of 60 is 1/2. Okay, raised to the third power. Okay, minus cosine of 0. Cosine of 0 is 1. Okay, so we have 1 raised to the third power. So simplifying further gives us negative 1 over 6 times the quantity 1 over 8. 1/2 raised to the third power is 1 over 8 minus 1. Okay, which will give us minus 1 over 6 times 1 over 8 minus 1 will give us negative 7 over 8, right? Negative 7 over 8, and minus minus gives us positive. Therefore, the integral is positive 7 over 6 times 8 is 48. So the double integral is equal to 7 over 48. Okay, so we were able to show 4 examples, okay, 2 where the region R is a rectangular region, and the last 2 examples, okay, is where the rectangular region is, where the region R rather, okay, where the region R is non-rectangular. Okay, so I hope that everybody can follow. And this time, let us consider to evaluate the integral of y e raised to x cubed dx dy, where x goes from y over 2 to 1 and y goes from 0 to 2. Okay, now if we will try to evaluate the integral of the inner integral, okay, in x, okay, y is temporarily held as constant. Okay, take note that we have the order dx dy, so we need to perform the inner integration first in x. And since y is temporarily held as constant, we will evaluate the integral of e raised to x cubed dx. And of course, we cannot simply evaluate the integral of e raised to x cubed dx since u is x cubed and the differential of x cubed is 3x squared dx, and x squared is nowhere in the integrand. Okay, so it will give us a little difficulty when evaluating the integral of e raised to x cubed dx. Okay. Okay, therefore, we can try reversing the order. Okay, so meaning from the differential of a equals dx dy, we will reverse the order to dy dx. But of course, when we reverse the order, okay, we will consider also changing the limits, no, corresponding to the inversion of order or the reversion of order. Now, how do we do it? Okay, so in here, the region R, okay, the region R is x going from, okay, x going from y over 2 to 1, okay, and y goes from 0 to 2. Okay, since we are going to reverse the order, we have to look at the geometric representation of the region R in the xy plane. So how do we do that? Now, consider the interval of x going from y over 2 to 1. So if x is, okay, let me use other color. If x goes from y over 2 to 1, it is actually based on the two equations, x is equal to y over 2 and x is equal to 1. Now, when x is equal to y over 2, okay, equivalently, we can write this as y is equal to 2x. Of course, y is equal to 2x is a line passing through the origin. So if we will draw it in the xy plane, if we will have the sketch of y is equal to 2x, this is the x-axis and this is the y-axis. Okay, x goes from y is equal to 2x. Okay, it passes through the origin. If x is equal to 1, no, let us say that this is 1. When x is equal to 1, of course, the corresponding value of y is 2. 1, 2. Okay, so this is it. Okay, so when x is 1, y is equal to 2 times 1, which is equal to 2. So this is the point. This is 1, 2. And if we will draw the line, okay, this is actually the line y is equal to 2x, or x is equal to y over 2. And the line x is equal to 1 is this. Okay. So this is actually the region R. Okay, now please take note that if we will consider any horizontal line drawn here, x will go from the left is y is equal to 2x, or x is equal to y over 2, to the line x is equal to 1. Okay, this is also x is equal to y over 2. And this is similar to x left to x right. And x right is x is equal to 1. So x will go from y over 2 to 1, from left to right. And y, of course, will go from, okay, let us draw any vertical line. Y will go from where? From y is equal to 0 to the uppermost, y is equal to 2. So y goes from 0 to 2. Okay, got it? Now, this is when, okay, this is when we do the order dx dy. Okay, and it seems that it is not horizontally simple, since we cannot easily evaluate the double integral in x first. Okay, okay, therefore, uh, we have to change the order. And if we will change the order, okay, we can take the differential of a is equal to dy dx. Okay, so we are going to do the upper vertical integration first, from lower to upper, then horizontal. Okay, so if we will get the region R, if we will express the write the region R in the order dy dx, y will go from 0. Okay, so y goes from 0 to the upper. Okay, and the upper is determined by the line y is equal to 2x. So y will go from 0 to 2x. Okay, take note that if we will draw any vertical line, the lower point is determined by the x-axis, so y is equal to 0, and the upper point is determined by the line y is equal to 2x. So y will go from 0 to 2x. Now, what about x? So we go lower to upper, so this time we will go left to right. And the leftmost value of x is 0, and the rightmost is 1. Therefore, x will go from 0 to 1. Okay, and this becomes the new limits of integration. Hence, going back to the problem, if we are going to evaluate the integral, okay, we will evaluate the double integral of y e raised to x squared dx dy, y going from, x going from y over 2 to 1, and x going from, y going from rather 0 to 2. If we are going to reverse the order, okay, let us reverse the order. So that gives us y e raised to x cubed. Okay, instead of the differential of a equals dx dy, we will do it dy dx. So dy dx, the inner variable of integration is y, and this time y goes from 0 to 2x. So 0 to 2x, and x will go from 0 to 1. Okay, so this will be the basis of the new limits of integration corresponding to the reversion or inversion of order. Okay, so if we are going to evaluate the integral, the inner integral, okay, in y, x is temporarily held as constant. Therefore, e raised to x cubed is a constant. So we integrate y dy, and the integral of y dy is y squared over 2. So that gives us the constant e raised to x cubed. Okay, integral is y squared over 2, and we have to evaluate this from the lower limit y is equal to 0 to y is equal to 2x, okay, then times the differential of x. Okay, so if we will evaluate the integral, okay, we have the integral from 0 to 1, okay, we can bring out 1/2 before, or write 1/2 before the integral sign. Let's do it. So this is equal to 1/2. Okay, we factored out the constant 1/2, and we have e raised to x cubed, and when y is equal to the upper limit at 2x, y squared is 2x raised to the second power. Okay, so 2x raised to the second power. Okay, and when y is equal to 0, everything is 0. So minus 0 times the differential of x. And look at what happens. Okay, we have 1/2 integral from 0 to 1. We have e raised to x cubed. Now, 2x raised to the second power is 4x squared dx. And if we will write 4 before the integral sign, that gives us 1/2 times 4 integral from 0 to 1 of e raised to x cubed times x squared dx. Okay, of course, 1/2 times 4 is 2. So we will have 2 times the integral of e raised to x cubed times x cubed dx. And we can evaluate the integral by using the formula. The integral of e to the u du is e raised to u. And take note that if we will let, okay, in here, if we will let u is equal to x cubed, each differential, of course, is 3x squared dx. But we have only x squared dx here. So there must be a correction factor 1/3. So that gives us du over 3 is equal to x squared dx. There is a correction factor 1/3. Okay, so we write the correction factor 1/3 before the integral sign. So 2 times 1/3. And the integral of e raised to u du is e raised to u. Okay, so e raised to x cubed, okay? And this must be evaluated from the lower limit 0 to the upper limit 1. Hence, evaluating the integral, we have 2 times 1/3 is 2/3, okay, times when x is equal to 1, that will give us e raised to 1, or simply e, okay, minus when x is equal to 0, that gives us e to the 0. But of course, e to the 0 is equal to 1. Hence, the double integral is 2/3, okay, times the quantity e minus 1. Okay, so this is the integral of y e raised to x cubed dx dy, okay, where x goes from y over 2 to 1, okay, y goes from 0 to 2, but when we evaluate the integral, since it gives us difficulty in evaluating the integral in this order, we have to do inversion of order. So we reverse the order from dx dy to dy dx. But corresponding to the uh, inversion of order, there is change of limits, okay? And we base the change of limits on the representation or on the sketch of the region R. Okay, so initially we had uh, the differential of A equals dx dy. So we go horizontal first, okay? X is equal to y over 2 to 1, and then y going from 0 to 2. But since it gives us difficulty, so we had it the differential of A equals dy dx. So vertically simple. It is vertically simple. It will be more convenient to do it uh, integrating in y first, no, then in x. Okay, so y will go from lower to upper. Okay, so the lower is y is equal to 0, and the upper is y sub h is y is equal to 2x. So we write y goes from 0 to 2x. And then we go from left to right. And the leftmost value of x is at the origin. So at x is equal to 0 to x is equal to 1. So this is 0, 0. Okay. So x will go from 0 to 1. So that is the reason why we had the interval where y goes from 0 to 2x and x goes from 0 to 1. Okay, which is very convenient now to evaluate. Okay, so in our next discussion, we will consider some application of double integrals, and we shall show application on how to find the area by double integration, and then eventually find the volume of solid by double integration. See you in our next discussion.